Hello everybody, let us start this module 3, that is specifically in solidification and casting process. As we have already explained the nucleation process and the growth and the different growth processes also in the last module, but of course some kind of understanding is required in the what we have explained in the last module to understand the solidification and casting process. So, this particular module will try to cover up the first is the formation of the planar front, plane front, then what the different columnar equiextend dendritic structure forms, and what can be the conditions in terms of the solidification parameter such that existence of the planar front or some kind of the instabilities persist during the solidification. That will try to explain in this particular module, and finally we will try to look the segregation in ingots and casting process, and some kind of the demonstration of the casting process in terms of the solidification behavior we will try to explain this particular module. So, let us start with this thing, very basic understanding that definitely that when you try to discuss the solidification in casting process, so it is finally linked with the mechanical properties of the cast products. So, that is why we are trying to understand the different aspect in the solidification process associated with the any kind of the in general the sand casting process. And we see that mode of solidification is basically decide or maybe link with the final microstructure and morphology of the solidification, and in that sense, if we try to understand the final microstructure or morphology associated with the solidification in casting process, then we try to look into what are the nucleation and growth occurs in specific to the casting processes, and what can be the instability conditions we can prevail during the movement of the solid liquid interface in a solidification process. So, we start with the very basic things that we know, the time temperature diagram I have shown here. Here the in case of the pure metal, we can see this is the first figure, the pure metal. This indicates the time versus temperature diagram, and here you can see the melting point is 1, but one single melting point temperature, but the changes of the phase from liquid phase to solid phase occurs over a span of the time. So, that is the indicative of the in case of the cooling curve of the pure metal, but if it is an alloy system, then we can observe that this solidification occurs over a range of the temperature, that is between the liquidus and solidus temperature, and here we found there is some slope exists between these two. So, that slope exists, but it also happens over the time, over certain period of the time. It means that solidification to perform this thing, it takes some period over which the solidification change, during solidification there is a change of the phase from the liquid phase to the solid phase. So, with reference to this cooling curve, we can try to understand that how to look into the cooling curve for the binary alloy, and try to link with the temperature versus composition in case of the binary system. So, if we look into that, suppose we draw the time versus temperature diagram for different composition of an alloy. We start with the pure metal. So, pure melting point, that single melting point, but over a period of the time there is no slope here. So, that it means that it is a 100% A. So, I can say this 100% A, that means it is a pure metal, and this is a typical cooling curve. Similarly, if 100% B, that is the in the binary alloy, the another component or another element, 100% B, it is also pure, and having the B is having the lower melting point than A. So, once we identify these two cases, these two, and we not corresponds to not having the zero slope in these two cases, because we observe the melting this cooling curve, there is a transition from liquid phase to solid phase without having any slope. It means the single melting point temperature exists for pure metal. So, pure A and pure B, we can identify their melting or solidification, that solidification temperature. But if there is an alloy, for example, in between some mixture of A and B, certain composition, certain percentage of the A and remaining percentage of the B, if it forms, then this binary alloy, and we start this, we look into the cooling curve also, that starting from the this liquidus temperature at it end, the solidification ends in the solidus temperature, and it exits some slope is there, and this slope depending upon the whether melting point A and B, we can, the slope can change, it can be positive, it can be negative slope also. So once we get the slope, and similarly if we change the composition, so A plus B, the different proportional way, change the composition, and in that case we can see that we can identify the different points, and if we join it this thing, then we will be able to get this time versus composition. So here, sorry, temperature versus composition diagram. So here temperature for pure metal A and temperature for pure element B, and in between the any particular composition, this is the liquidus temperature and this is the solidus temperature for a particular composition, say this is the C0, and C0 means, the C0 composition means that C0 composition for B and remaining is the A. So this way, once we construct this temperature versus composition diagram, and here we can see that we are assuming that both are, when you are mixing the element A and B, we are assuming that they are completely soluble with respect to each other, and then in that sense we can draw this temperature versus composition curve for binary alloy, only two elements are there. So we want to construct this diagram, then we can further utilize this diagram for the other purposes. Now I come to this point, that solidification in casting process. So in general we can see that we start with the liquid phase, and within the liquid phase there is a nucleation occurs, and nucleation, and gradually this try to grow this thing, and finally once there is a change, it is here the complete liquid phase, and here the liquid plus solid phase, the mixture of that, and it is completely solid phase. So this is the steps associated with the solidification, starting in the liquid phase, and there is a through the nucleation and growth mechanism, it finally reaches to the completely solidified component. So but in these steps we have already discussed that definitely the first step of the any solidification is the some nucleation should start. So nucleation should start, and in that case the driving force for the nucleation is mainly the undercooling or the supercooling. Now here the phase transformation occurs in the two steps. We can see that first nucleation occurs and then growth. So nucleation and growth occurs together. So that's why we say this phase transformation is basically two steps. We need to look into the different nucleation theory we have already discussed, and then after nucleation, then we try to look into the growth mechanism. So based on that, the complete solidification process of an pure element or alloy system can be explained. Now we can see that nucleation involves the formation of the small stable particles. So we have already find out the conditions for the stability of the size of the nucleus, critical size of the nucleus. So small stable particles forms, and of the new phase from the liquid. See, this is liquid phase, and in the solid phase are formed. So that is nucleation, first nucleation forms, and gradually the remaining part of the liquid is converted to the solid phase in between stage. But in the growth stage, the stable nucleus will only allow to grow. But in that case, the unstable nucleus which is formed, that actually disappears, and finally once they try to grow the stable nuclei, then as a result the parent metal completely, the liquid phase is completely disappear, and then it becomes completely the solid phase. So this is the simple way we can understand the solidification, in general the solidification, and of course I can say the solidification in casting process, because anyway solidification is associated mostly the casting and welding process. So here we are discussing the solidification for the casting process. Now I am just making some recap of this nucleation and growth as so that it will better to understand the completeness of this particular module, to understand the solidification behavior in case of the casting process. So progress of the phase transformation already discussed, is two phases, nucleation and growth, we know that nucleation is the homogeneous nucleation process and heterogeneous nucleation process, and in both the cases the driving forces are different. In case of the homogeneous nucleation process, it is basically from the critical size of the solid forms from the liquid phase, and here the driving force is mainly the degree of undercooling, and mostly in ideal situation it is without any kind of the external interface. So, that is the basic theory of the associated with the homogeneous nucleation process. So, degree of undercooling, we understand that this is the equilibrium solidification temperature. Now, if it is in certain, there is a localized position, this temperature can reduce below the melting point temperature. So, this its particular temperature T at this optimum point, and then it is a melting point Tm. So, that difference between these two is basically known as the degree of undercooling. So, that occurs during the solidification. So, and we say then the homogeneous nucleation process, this is the main driving force to start the nucleation. Now, when you try to understand the homogeneous nucleation process, so it is a nucleus forms in the form of a solid particles. We are assuming it is a liquid phase to solid particles. When you try to grow or develop from the liquid phase to the solid particle, so we can look into the Gibbs free energy available to form from liquid phase to the solid phase. So, already we have discussed in the last previous modules on the I think module 1 or module 2, the how to calculate the Gibbs free energy associated with that, but till here two different things are there. One is the when solid particle forms, so it is associated with the it is a volume free energy. So, that means some volume free energy, and we are assuming it is a spherical volume. So, the one is the volume free energy, another is the surface free energy available. So, because when there is a surface energy will be associated when making some surface spherical particle. Now, if we track this this thing total free energy change in terms of the volume free energy and the surface free energy available. So, here we can calculate this thing, the volume of the spherical particle, assuming it, we are assuming it is a the size of the shape of the nucleus as a sphere. So, therefore, volume of the sphere is 4 by 3 pi r cube, r is the radius of the sphere, and the delta GV is the volume free energy, and it is explained per unit volume. Similarly, gamma is the surface free energy or specific surface energy of this particle. So, only one particle will be created from liquid phase to solid phase, it will be associated with the surface as well as the some definite volume will be there. So, surface energy per unit area and 4 pi r square is the surface area. So, therefore, it counts the total free energy change due to the formation of the one nucleus having radius r. Now, when you try to find out what can be the critical size of the nucleus which will be stable, then in that case we can find out this find out the optimum size delta G by dr. So, equal to 0. So, basically we are trying to find out the optimum values of the r. So, it exists when the change of the free energy with respect to r equal to 0, and that corresponds to the critical size of the nucleus. So, that means r equal to r star. If we do this exercise, we will be able to get the critical r star equal to twice gamma by delta GV. So, gamma is the specific surface energy of this particle and it is a volume free energy, delta GV is the for this particle, and we can find out what is the critical amount of the energy, critical size of the nucleus associated with the total critical values of the free energy change. So, critical value of the free energy change delta G star can also be calculated in terms of the free energy, that gamma square and the delta GV square. Okay. And further we can calculate that delta GV volume free energy in terms of the latent heat of this particular material, degree of undercooling, and in terms of melting point temperature. So, in this case delta GV we are calculating, we are assuming the degree of undercooling is basically is very close to the melting that means is close to 0, that means near to the melting point temperature, actual temperature, because here we can see delta T equal to Tm by T, but T is the very close to the melting point temperature. So, latent heat and equilibrium equilibrium solidification temperature, or Tm indicates the equilibrium solidification temperature, or other way we can assume this as equivalent to the melting point temperature. So, with this calculation we can find out that this is the values of the critical values of the this energy, so that for the stable nucleus, and corresponding radius is the critical size of the nucleus. So, this sample calculation we already discussed in the nucleation theory, but now if we try to look into the heterogeneous nucleation process, here the formation of the critical size solid from the liquid on the pre-existing sites, that means some surface or interface the nucleation processes start. So, that means in that case definitely to start this heterogeneous nucleation process, the energy barrier, the energy required to start this process is less as compared to the homogeneous nucleation process, because in this case nucleation start with some pre-existing surface. So, in general we can say that it is a this red color graph is basically so for heterogeneous nucleation, and is the blue color is basically homogeneous nucleation process. We can see almost, because in this case the critical size of the nucleus in both the cases homogeneous heterogeneous it is the same, the R star value, but amount of the critical amount of the free energy change are different. In this case definitely heterogeneous nucleation process it is less as compared to the homogeneous nucleation process. We can relate it, the delta G star heterogeneous nucleation process is equal to delta G star homogeneous as a function of S theta, but S theta the shape of the nucleus, because in homogeneous nucleation process we are assuming it is a complete spherical particle, but when heterogeneous nucleation process nucleation start from pre-existing surface, so it may not be the complete sphere, it is a part of the sphere. So, here now it is basically S theta, this is represented by the shape factor S theta, and S theta must be between 0 to 1. So, definitely when it is less than 1, then heterogeneous the energy barrier for the heterogeneous nucleation will be much less as compared to the homogeneous nucleation process. So, these are the two types of the nucleation process. Once nucleation starts, then we try to look into the what way the interface moves, the solid liquid interface moves, and that will something in the other way it is very complicated in case of the alloy system, because in case of the if you try to understand the solidification in the alloy system, so here you can see that liquid of uniform compositions is basically rarely uniform after solidification. Why it is like that? Because if you look into that, most of the cases during the solidification of an alloy system, there is a redistribution of the solute is exactly happens. So, we can take a simple example for that. We see the temperature and solute concentration. So, x axis and y axis. So, this is the solute temperature, and we just look into the part of the binary phase this diagram, the temperature versus composition diagram, and part of this we can pick up, and you can see we have observed this is the liquidus line, this is the solidus line. So, I am just trying to relate it this way, that this diagram. So, this diagram. So, here it is the liquidus line, this is the solidus line, and we can take part of this thing, and that is represented here, we just picked up here. So, here we are assuming the initial composition, we just pick up any initial composition of the alloy equal to C0, called solute concentration equal to C0, this thing, and C0 corresponds to that, this is the liquidus line and this is the solidus line, and for the simplicity we are assuming this is the liquidus and solidus lines are straight lines. Now, C0 composition it starts assuming the solidification starts at this point, because at this point above that temperature it is in the liquid phase. So, when it is come to this point, liquid phase is converted to the solid phase, but in case of the alloy system it basically passes through this temperature, lowering the temperature, and when it come to this point ideally the solidification completes. So, basically between the TL and TS the solidification starts at the point liquidus temperature TL, and solidification ends in the solidus temperature at TS. Now, in between that it passes through the certain temperature, for example in between it can passes through one particular temperature T. Now once it is in a particular temperature T means, in that case the it is not completely 100% solidified. So at temperature T the solution exists in the form of a mixture of the solid and liquid phase. Now when it is a mixture of the solid and liquid phase, but assuming at this temperature mixture of the solid and liquid phase, but in this at particular temperature T, liquid phase having composition Cl, liquid phase, because this indicates the composition of liquidous line, the composition, because the liquid phase and the composition should be Cl. So that means this composition of the Cl, that means liquid phase composition is which is more than that of the initial composition C0. In other way, the what can be the solid there in within the mixture, then solid part it should have the composition Cs if it is follows the solidus line. So Cs, but Cs, the in this case is the Cs, the solute concentration for the solid phase, which is less than that of the C0. So that means the over the when there is a temperature changes between the TL and Ts, gradually temperature reduces, there is a continuously changing of the composition between the solid and liquid phase. Now under equilibrium conditions, so when you are allowing diffusion to occur of the in the liquid phase and the solid phase both, then it will exactly following the, in ideal situation, the following the solidus and liquidus line. But in practical case this it may not be under equilibrium conditions, rather I can say that the different conditions we have already explained, that there is, assuming there is no solution diffusion in the solution in the solid phase and the liquid phase in the, there is no solution in the solid liquid phase, and in that case the liquid phase will be following the line along the liquidus line, so, and the solid phase will be following the solidus line. So there is a temperature decrement is there, there is a continuously changing of the composition of the solid and liquid phase. But if you do not allow no diffusion to occur in the solid phase, or in that cases allowing the diffusion in the liquid phase, in that case there might be changing the equilibrium, the temperature might be changing or may not be having sufficient time to diffusion to occur either in the solid phase or the liquid phase. I mean to say that in practical situation it may not follow exactly the solidus and liquidus cases if it is other than the equilibrium solidification condition. So that is why this composition is continuously changing between the liquid and the solid phase, and we can based on that, so we predicted the different assumptions, and we predicted the theory that we have already explained. So at particular temperature solidification occurs and then composition changes. So we can say there is a redistribution of the solute is exactly happens during the solid and liquid phase. But overall you can say the redistribution of the solute, it actually depends on the thermodynamics. That means the phase diagram means this diagram where the liquidus line, where is the solidus line with respect to the composition, it depends on that, as well as the kinetic, that means what is the extent of the diffusion to occurs and what is the degrees of undercooling is available, all actually matters. And of course the fluid flow means in the sense the reduced, because then there is a concentration gradient is there, so there may be the flow of the liquid metal during from one position to another place, and mostly it happens in the micro scale. So all this matter to redistribute the solute concentration during the solidification. So that's why we are telling the liquid may not be the uniform composition during the solidification for an binary alloy system. Now further we can study this diagram and try to look into the what we can utilize the phase diagram to find out the interface stability conditions also. So phase diagram, we are assuming the initial composition C0, that we already explained this thing. Solidification starts at temperature TL, at temperature T, any particular temperature T, we can see the Cs and Cl are the composition of the solid and the liquid, and that actually happens at the solid liquid interface. Now at any equilibrium temperature T, what will happen in the liquid, I already explained that equilibrium temperature T, this is the Cl and Cs are the this composition of the solid and liquid. But in that case, what depending upon the diffusibility in the liquid phase for the solute, or in the solid phase, there is we can define the partition ratio or the equilibrium segregation coefficient, and with respect to the Cl and Cs, the composition of the solid and the liquid phase between the range of the liquidus and the solidus temperature. So, at particular temperature T, K, the partition coefficient is defined by the Cs and Cl. So, usually partition coefficient is the less than 1. Okay, and of course, it depends on this thing what way we are considering the temperature versus solid concentration, or this diagram, because this diagram we have shown the negative slope of the liquidus and solidus line, but it may happen so we can construct the diagram having the positive slope liquidus and solidus. In that case, definition of the K and the values of the K can be different what is the as compared to with respect to this particular diagram. So, in this particular sense the K should be less than 1. So, all this matters. K, we define the segregation coefficient between these two. So, it actually depends on the it can vary, the values can vary depending alloy to alloy system, dependent alloy system, but usually less than 1. Now, if we study this diagram, what can be the conclusion from this diagram we can form it. First is that solute content of the liquid is continuous to rise during the solidification. It is very obvious from this diagram, the solute concentration in the liquid phase is definitely it is rise, it is in the increasing order, and lowering the solidification temperature, but at the same time even the solid grows from the liquid, its solute content Cs also continues to rise. Here also we can see the Cs also, the initial values of the this Cs with respect to temperatures, the Cs also is also growing, okay, but Cs can grow up to the C0, but Cl can grow which is above the C0 to some other values. So, K less than 1 with reference to this particular diagram, and Cl and Cs both increases at temperature of the solid liquid interfaces drops during the solidification. So, during the solidification temperature drops, both Cs and Cl both are increasing, and as per the nature of this particular diagram. Now, if we define the slope of the liquidus line is ml, if it is known, which is also less than 0. So, because it is a negative slope, if you see the diagram it is a negative slope. So, the slope of the liquidus line we can assuming it is a negative slope, it is ml, and of course, K also less than 1 and less than 0, and when K less than 1. So, here I told you this is this slope is less than 0, there is negative slope, but in that case K less than 1, but if it is a positive slope diagram then K should be greater than 1. If the liquid line is straight line, we are assuming this thing. So, at temperature T on the diagram line can be expressed like that, because here is just simply the any kind of the T y equal to, we use the straight line equation y equal to mx plus c. So, here c equal to y equal to is variable temperature, variable the y axis temperature T, and then slope is ml and the m, and values of the x equal to the value is Tm, this is the intercept, sorry, Tm is the intercept, but Cl is the composition, is the the liquid composition is the Cl is the variable here, that is the x variable, because x axis represents the composition, concentration or composition, and intercept along the y axis, that is the C, which is equivalent to Tm here, starting with that point. So, this way we can simply represents that any temperature in terms of the composition, slope available, and melting point temperature. Now, further study this diagram, in this case actually we are looking into the complete diffusion in the solid and liquid phase we are considering to easily understand the situation, and of course, this is the condition for the equilibrium solidification. Now, under equilibrium solidification means you are allowing the diffusion to occur both in the solid and liquid phase, such that when the lowering the temperature, it will be following exactly the solidus and the liquidus line. Now, if you are assuming that Fs and Fl in the particular point, the fraction of the solid and liquid fraction in the mixture between the solid and liquid zone, in that case we can see that conservation says that total fraction should be 1. So, that is why Fs and Fl liquid fraction and solid fraction total 1, and here we can see the solid and liquid phase, the planar front is basically moving, towards the liquid phase. So, gradually solidifying occurs, solidification occurs, and this front is moving towards the liquid phase. So, now we can see that we can, in terms of the composition and the solid interface distance, we can put it, we can plot it. Here you can see Cs is the composition of the solid, definitely concentration of the solid is less than that of the C0, we observe from the diagram, and Cl is the, which is more than the more than of the liquid phase. So, Cl is the composition of the liquid phase, and this thing, and it's a, because we are allowing complete diffusion to occurs. So, therefore, it is represented by the straight line. Now, this is the solid phase and liquid phase, and this is the interface. So, that area actually represents the total amount. So, therefore, area Cs Fs and Cl Fl, amount of the solute in the solid and the liquid together. So, here amount of the solute Cs Fs into Cl Fl, that is the amount of the solute in the liquid solid phase and the liquid, the solid and the liquid. Now, with reference to the initially, it is starting with the C0, initial composition of C0, or I can say that this actually C0. So, therefore, this area. So, initially C0 with reference to C0 into total fraction liquid and Fs, but of course, Fs and Fl in the, when the C0 composition, it was completely liquid phase. So, then Fs plus Fl equal to 1, it was Fs was 0 and Fl equal to 1. So, therefore, Fl equal to 1, that it becomes C0. Now, this is the balance. So, area represents the amount of the solute in the liquid before solidification, total amount of the solute before solidification, which is equivalent to this amounts of the solute in the liquid and solid together. Make it equal, we get one equation from here. Then if we apply the lever rule also, and we use this equation also, the partition coefficient, and from there we can get the composition of the liquid. But how to apply the lever rule here? We are assuming the composition is basically C0 is the intermediate, and here composition is the Cl, and here composition is the Cs, which is less than C0, and Cl, which is more than C0. So, therefore, we know if we apply the lever rule, therefore, the liquid fraction Fl, liquid fraction is the difference between these two, this liquid fraction, this side is the liquid fraction. So, here C0 minus Cs by Cl minus Cs is the liquid fraction, and solid fraction Fs equal to the other side Cl minus C0 by Cl minus Cs. So, this way we can calculate the solid and liquid fraction by applying the lever rule. These two equations you can utilize, this equation you can utilize, then we can find out the composition of the liquid in terms of the initial composition C0 concentration, and in terms of the liquid fraction partition coefficient, we can easily express we can easily find out the composition of the liquid phase. So, at the same time we can find out the composition of the solid phase in the mixture also by utilizing these equations. Now, no solid diffusion and the complete diffusion in the liquid phase, that we have already discussed in the last module, and of course, at the same time no solid diffusion and limited liquid diffusion also we have discussed in the last module, both the cases, and we can see that how the composition varies when the solid liquid interface or away from the solid liquid interface during the solidification process. So, I am not repeating this part here. Now, if we try to look into, just once we understand the what way the solidification of the alloy system is happening in this particular casting process, now we try to understand what are the different modes of the solidification just overall. So, therefore, solidification modes, we can see that during solidification pure metal, the solid liquid interface is usually planar, but that is not always true, but usually planar interface usually in case of the solidification of the pure metal. But for an alloy system, there is a chances is much more, the solidification in the solid liquid interface, it can be planar, it can be cellular, it can be dendritic, depending on the solidification conditions and the material system involved. We will try to explain the what can be the solidification conditions such that planar, cellular or dendritic structure will form, or it will try to form that kind of the structure, not the, or what conditions prevail such that planar front will be formed or solid liquid form during the solidification process. that we will try to look into. Now here you can see that if we look into the 4 basic types of the solidification modes, the planar front is moves this way, the plane in the form of a plane, it moves this thing, and otherwise there is instabilities are there, it will create the cellular type of the structure, and of course depending upon the supercooling, constitutional supercooling, this the cellular, the spacing of the cellulars can be different. There is also even the similar way, the columnar dendritic is basically it forms the dendritic structure, one primary arms is there and the long primary arm is directed one particular direction, that creates the secondary arm, and we see the columnar dendritic means that one primary is relatively very big one in particular directions as compared to the secondary or tertiary dendritic arm. So it can create this kind of the structure also. And then other is the equiax dendritic structure, usually from equiax dendritic structure, it is dendritic structure, but there is the primary arm, secondary arm forms in such a way it looks like a one equiax kind, similar kind of the equiax kind of the structure. Here you can see this type of the structure is formed. So a consisting of the primary and secondary dendritic arm. So that is why here also you can see the similar kind of the structure is formed. So almost similar size. So this is called the equiax dendritic structure. But of course, what type of the structure, basic solidification modes, we try to understand the instabilities associated with the solidification process. Then we can find out the condition to form the basic solidification modes associated with the casting process. Now we coming back to this one particular, although that discuss the interface stability associated with the solidification in casting process. Here we can see the 2 different cases we consider. One is this in terms of the temperature gradient in the solid and the liquid phase, and in these 2 cases, these 2 are the different, and one case, first cases it will creating the planar interface, other case it creates some kind of the instability associated with that. Now we look into this particular point here. For pure substances there is no constitutional supercooling, or there is no this changing of the concentration in the solid and liquid phase in the mixture of the solid, that kind of the phenomena is not associated with in case of the pure metal. So therefore here no constitutional undercooling is available, and that creates therefore whatever instability conditions arises in case of the pure substances during the solidification of the pure substances, it becomes only of the thermal field. So only temperature actually govern or decides the instability condition associated with the pure metal. But in case of the alloy system, the instability brings both the temperature conditions as well as there is a concentration gradient, or maybe the concentration of the alloy system, or I can say that the constitutional supercooling, because anyway constitutional supercooling is there is a change of the composition during in the solid liquid mixture during the solidification process of an alloy. So that actually brings the different instability condition associated with the solidification of an alloy system. Now you can see that solidification usually starts from the mold wall, and then we just try to look in what way the solid liquid interface moves, and it will try to move towards the liquid phase. So that is the simplest way, the understanding of the solidification or movement of the solid liquid interface during solidification. Now if the temperature at the solid liquid interface is equal to the solidification equilibrium solidification temperature, so that means which temperature solidification occurs. If that is the case, then in that case the interface is equilibrium. Interface is equilibrium and it cannot move or cannot create the instability there. Now definitely in pure metal, pure substances, usually undercooling is required to drive the process to move the solid liquid interface one particular direction. So the driving force is the undercooling in this case, but the thermal instability should grow at the interface where temperature is higher than its melting point. When the temperature in this particular zone, when the temperature is higher than its melting point, at this point the thermal instability usually occurs, or thermal instability should grow. It means that if the planar front is not stable there, the instability create some kind of the perturbation is created one particular position, and it will further modify the temperature gradient and the heat flow direction also, or heat flow rate of the heat flow, then another perturbation will be created, and then it creates kind of the different kind of the cellular or dendritic kind of the structure. So what that instability is, so therefore we can say that in case of the pure metal, only thermal instabilities can occur with two different ways, two different possibilities the thermal instabilities can occur. One is the planar, that means planar is we consider as a stable interface, and when the thermal gradient is positive, here you can see the thermal gradient is positive, that means this in the solid thermal gradient is positive, these cases it is positive temperature gradient, and you can see the heat flow occurs this way and it creates the planar interface. But other cases dendritic equiaxed kind of structure can form. In that case the interface become unstable. So when thermal gradient is negative, so when thermal gradient is negative, here it is positive temperature gradient and negative temperature gradient on the at the solid liquid interface. In that case the instabilities occurs and it creates kind of the this kind of the dendritic structure which is different from the planar structure. So this is the this situation may arise. So but usually planar interfaces occurs in case of the pure substances, but at the same time dendritic equiaxed structure may also form associated with the pure metal. But all these cases it's a the instability is exactly governed by the only the temperature conditions. That means there is no kind of the compositional changes doesn't influence in the instability condition in case of the pure metal. Now if we try to look into the interface stability in case of alloy system, we can look into this particular point, because interface stability for an alloy system it's actually governed by the compositional field, changes of the compositional field, concentration gradient in front of the growing interface. So in front of the solid liquid interface what kind of the compositional changes occurs, that actually influence the different instability for an alloy system. So when thermal gradient in the liquid at the solid liquid interface is smaller than the liquidous temperature, it becomes more stable. In the liquid temperature gradient, then that condition actually creates more stable situation. In that case the liquid at the interface is lower temperature than its liquidous temperature. So liquid at the interface is at the lower temperature than that of the liquidous temperature. So it becomes more stable. So therefore the liquid is constitutionally supercooled where instabilities will become stable. Even the instabilities occurs and create some kind of perturbations, but that become stable and create kind of the dendritic structure, but it will continue to grow even in that case. But I mean to say that liquid at the interface at the lower temperature than the liquidous temperature, it creates more stable situation, even there is having constitutional supercooling also, but constitutional supercooling the changes is there, but the interface becomes more stable in this particular situation. So in that case temperature will be lower than that of the equilibrium temperature. In that case that temperature is usually less than that of the equilibrium temperature. Now the other way, when the thermal gradient in the liquid, the just opposite, thermal gradient in the liquid at the solid liquid interface is greater than that of the liquidous temperature gradient, the interface will remain planar in that cases. So interface will be remain planar, but in that case the small constitutional supercoolings, the instabilities is try to grow in the solidification direction. So in that case here the constitutional supercooling will play the role, and depending upon the degree of the constitutional supercooling the different structure will form. So here the instability will grow in the solidification direction, and as a result cellular interface will form. So we already seen, even if it is more constitutional supercooling, then because of the lower thermal gradient the spacing between the cells also increases. So low temperature thermal gradient but relatively more constitutional supercooling, that really increases the spacing between the this cellular structure, the spacing between the cellulars, that actually increases if the supercooling is constitutional supercooling is much more. But if it is further, even it is more further, it is very high the constitutional supercooling, then the equiaxed grain structure is basically promoted and it is nucleated in the liquid away from the interface. So away from the interface, more or less that there the equiax gains will usually form in this case. So, I mean to say that here this both will play the role, the temperature gradient and the constitutional degree of the constitutional supercooling, they play the role to bring the interface stability condition associated with an alloy system. So, usually very high values of the constitutional supercooling, that will promote kind of the equiax structure, even low values of the constitutional supercooling, that will create kind of the cellular structure, or even there is no constitutional supercooling, it will try to create kind of the planar structure. So, that is the overall understanding in the interface stability in the simplest way in case of the solidification of the alloy system. Now, here you can look into the further, try to find out the mathematically the what can be the conditions as in for the interface stability. Here is the constitutional supercooling, it actually usually occurs during the solidification, we know, and that is the due to the compositional solid changes, and results in the liquid is basically lower temperature than the actual temperature falling in the solidus but liquidus line. And here the it's basically all happens due to the in front of the solid liquid interface. Now, quantitatively we can describe the what can be the conditions such the breakdown of the solid liquid interface during solidification will breakdown means the planar interface will break down and during the solidification process. But before that, we try to look into these parameters. One is the diffusional coefficient of the solute in the liquid. So, diffusional coefficient of the solute in the liquid dl, we define this parameter, because anyway the constitutional supercooling is associated with the some sort of the diffusion to occur, extent of the diffusion occurs in the solid phase and the liquid phase. So, here the dimension is the L square by T, length square and time, I think, yes, time, and sorry T is the T indicates the time here, and R is the growth rate, the length per unit time, G is the temperature gradient, theta by L. So, all these parameter, the solidification parameters we define, R and G we can say is the kind of solidification parameter deal with the diffusion coefficient of the solute in the liquid. Now, what can be the conditions for the breakdown of the planar interface? So, here we try to represent the first figure. If you follow the first figure, temperature and concentration is there, solidus and liquidus line we have drawn, and degree of the delta T indicates the degree of undercooling here available during things, and this red zone is indicates that is the region of the constitutional supercooling. So, here you can see the compositional changes, or during the solidification it is not exactly following the liquidus line here. So, constitutional supercooling, the between the solidus and liquidus line we can follow this indicates the zone for the constitutional supercooling. Now, if we convert it into the T and distance from the solid liquid interface. So, here we can put it in the other way that this is the actual slope, and here this zone, red zone indicates the constitutional supercooling zone, that there is a compositional changes occurs within that zone. And here other way we represent this thing, you can understand the visibility will be much more if you look into this figure. Here you can figure there is a solid zone, solidified part and the liquid part, and in between there is a solute rich boundary layer. So, solute rich boundary layer we can see certain value, the solute rich boundary layer, this having certain value, the solid rich boundary layer, and solid liquid moves one particular rate, that is called the growth rate. Now, here you can see the solute rich boundary layer can be represented by dl by r. If you see what can be the dimension of the dl by r, dl equal to L square by T, and r is the L by T. So, T by L, which is equal to that unit of L. So, that is the that actually indicates the solid is the boundary layer it creates between the solid and the liquid phase. And here the slope of tangent, or basically this slope at this, when the constitutional supercooling state at this point, what is the slope of tangent? So, at any temperature, that is at particular temperature, then he can see that is a degree of undercooling delta T, the dy by dx, dx equal to is basically here dl by r. So, dl by r dy by dx, that actually indicates the slope at this particular point, but actual slope is the temperature gradient at this point, it is the g. Now, breakdown of the planar interface will occur if the actual slope, here you can see this slope is much more as compared to the actual slope g. So, g actual slope, here you can see the g indicates the temperature gradient at this point. So, and g definitely it is less than this other slope, this g is less than this. So, g is less than this, and g by r, we are getting this condition, g by r less than delta t by dl. This condition actually indicates the breakdown of the planar interface. We further analyze this part. So, shaded zone in the region of the constant supercooling, where liquid alone is the unstable there, and the here solid liquid coexist. So, in this particular zone, and in that particular zone, but ahead of the solidification front, they create some kind of the boundary layer, and that boundary layer can be defined by this diffusion coefficients of the solid in the liquid divided by the this thing growth rate. So, that actually defines the amount of the boundary layer between the solid and the liquid phase. Now, the thickness of the boundary layer can be at steady state situation can be expressed dl by r, that indicates the boundary layer at the steady state. Now, to avoid the constitutional supercooling, that means if there is no constitutional supercooling, then g should be greater than here. So, this constitutional supercooling, the disappearance of this particular zone, in that case the slope g will be always more than that of the other parameters. So, therefore, g should be greater than by delta t by dl by r. So, I mean to say that g is greater than equal to delta t by dl by r. This is another slope and this is the other slope, the temperature gradient. So, when there is a no constitutional supercooling, so g should be more or equal to that delta t by dl by r. So, therefore, to avoid the constitutional supercooling, g by r delta t by dl, it means that the planar interface will be stable at the steady state situation if there is no constitutional supercooling. I mean to say that here this condition indicates the planar stable solid liquid interface will be the stable. The other conditions what we discussed in the last slide, that g by r less than delta t by dl, that actually indicates the breakdown of the planar interface, that having certain amount of the constitutional supercooling. So, therefore, planar interface, solid liquid interface may break down to a cellular or further dendritic such that it creates kind of the solid cell or the dendritics. Therefore, they can coexist with the intercellular or interdendritic liquid. So, that means the interdendritic forms, but there is a between the primary secondary arms or with reference to the another dendritic arm spacing, there is a gap, at that gap the liquid may coexist. So, therefore, this solid liquid interface it can break down with these conditions. Here we can see that if you look into this growth rate and temperature gradient. So, here the higher g and lower r. So, higher g and lower r always leads to the stable planar solid liquid interface. Definitely, if g by r is much more, g is higher and r is lower. So, definitely g by r values will be much more. So, therefore, high values of the g by r ratio indicates that planar interface is more stable, or it actually leads to the stable solid liquid interface, planar solid liquid interface. But if the higher delta t, is, that means that this degree of undercooling or constitutional supercooling is much more, and higher values of the dl means the diffusion coefficient is much more. In that case, that actually leads to the more difficulty for the planar solid liquid interface to be stable. So, in that case, it brings towards the more instability conditions during the solidification of an alloy system. Now, once we create this thing, the solidification mode and different conditions, also we can say that there are different solidification mode we represent this way in terms of the degree of constitutional supercooling. We can say that it can create the planar, cellular, columnar dendritic and aqueous dendritic structure. We see there is the downward direction increasing constitutional supercooling, but here the planar definitely not having any actually not having any amount of the constitutional supercooling. So here the actual slope, this is the equilibrium and this is the actual slope indicates this one. Now cellular structure is there, so very small amount of the degree of constitutional supercooling is there in this case, and this side is the solid phase and the liquid phase, between these two and solidification front it creates them kind of the cellular structure. So but less amount of the constitutional supercooling is available. Now columnar dendrite little more than that of the previous one, it creates the columnar dendritic structure. If it is much more, then it will try to create the equiax dendritic structure. Actually, if you try to understand that what are the constitutional supercooling is associated with this particular alloy system, that actually decides what kind of the solidified structure you can prepare, with the equiax dendritic structure, columnar dendritic structure, cellular structure and planar structure, we can easily predict this thing. So therefore, the zone where the dendrites and the liquid phase coexist is called the Musi zone, that we know because already we have discussed. Now at very high degree of constitutional supercooling, the Musi zone becomes wide. So that means the constitutional supercooling is much more, that means we can create the Musi zone is much more, that means wide area, and that will promote is the equiax dendritic to nucleate. But at the same time, if the constitutional supercooling is much more, there might be other problem, the segregation may also happen. We will discuss later on if this constitutional supercooling zone is much more, what can be the other consequences in during the solidification of an alloy system. Here along with the mode of the solidification, we can merge with the effect of the cooling rate, because both are important to look into, because we already defined this R is the growth rate and G is the temperature gradient. This is the very standard parameter to understand the mode of the solidification. So now combining these two solidification parameters, we can say that temperature gradient and growth rate both are affect the solidification microstructure. Now product of G into R, we can see the multiply G into R, that actually is known as the cooling rate, and the ratio of G by R, which is determine the mode of the solidification. Then is planar mode, cellular, columnar dendritic. So we have already seen that instability condition in terms of the G by R. So G by R is basically represents the mode of the solidification, but G into R is basically represent the cooling rate, G into R. So these both parameters are important. So it's a mode of solidification, it's a cooling rate. Now how it represent this way, because G into R govern the size of the solidified structure. I mean to say that whether it is the fine structure, coarse structure will perform, that actually decided by the cooling rate. So G into R, and what will be the mode of the solidification, planar, cellular, that actually decided by the G by R. So here you can see that along the x axis we plot the growth rate, along the y axis we plot the temperature gradient. Now this indicates the low G by R this side. So that means, and here is the indicates the high values of the G by R. Now we can do separate divisions these things. So this high value of G by R is basically the mode of the solidification is usually planar, and low values of the G by R is basically equiax. So there in between the cellular, columnar dendritic, equiax and planar, these are the 4 divisions we can make it. Now if you take the cooling rate, overlapping the cooling rate, is this actually indicates the solid liquid interface here. So here the alpha is very high, here this line is indicate the alpha 1 and is alpha, this actually indicates G into R. So basically this G into R, that is simply representation of in the curve x into y equal to constant value. So in this thing G, so the similar way this is the representation of G into R, this curve. So this is the alpha 1. So here alpha 2 is, this is the low values of the G into R, and this is the high values of the G into R. So once it is like that G by R, so therefore high values of the G into R we are representing in terms of the alpha, it indicates the fine structure, it indicates the coarse structure, fine structure, very high values of this thing, and low values of the alpha 1 is basically coarse structure. So therefore higher cooling rate is basically fine structure will form, and the lower cooling rate coarse structure will form. So this way we can understand that this solidification parameters and how we can utilize the solidification parameters to define the mode of the solidification and the cooling rate together, and of course all this whatever we have discussed associated with solidification is definitely applicable to the casting process. But in very specific to the casting process, what kind of the microstructure is usually form and how it will relate to the solidification mode or solidification parameter, that we will try to discuss in the next class. So, for the time being, that is all for today. Thank you very much for your kind attention.